The mystery of the increased capacitance. Over his professional career, Tesla made many bizarre assertions, most of which have logical explanations. We want to focus today on number 5. The capacity of a body increases with height. He announced it in January 30th, 1901 in the New York Sun. Classically, the capacitance versus height varies almost hyperbolically here. As you raise the ball, it approaches its isotropic capacitance. We've learned over the years that if you do what Tesla said he did, you'll see what Tesla said he saw. Well, what was going on in this experiment that he runs at Colorado Springs? If you back up to 1896 or so, you can see he's actually running with a ball that he can raise and lower in his Long Island, in his New York laboratory. Here you can see the removable roof where he says I could pull the capacity up and down. In the photographs inside the laboratory, you can see a pulley just underneath the ball above the extra coil. Here you can see it in a little bit more detail. On May 29th of 1901, Tesla sketches this adjustable height ball. And here you can see he's actually got a piston that he's raising and lowering the ball with. And of course, this looks like a premonition for what's going to happen with the Wardenclyffe Tower. Here's the experiment that Tesla was running at Colorado Springs. He's got a 60-foot wooden tower with a wire running down. He can raise and lower the ball. At the bottom, he's going to have a coil. Here's the actual circuit that he's using. And he's got a variable frequency oscillator at this point to excite the base of this helical resonator. And he'll raise and lower the ball and measure, determine the capacitance from this. Here's the mystery. Capacitance doesn't go up as the ball is elevated. All right, well, how's he doing the experiment? Here's the capacitance bank that he's using, a regulating coil, back to a rotary spark gap, and the high voltage transformer that he's using. He gives you in the diary what the procedure is, and we want to focus here on this step 3, and you'll see that this is where there's a problem. Here's the procedure. He measures the inductance of the resonator at 138 hertz, which is the power line frequency going into Colorado Springs. He sets the height for the ball. He then adjusts his VFO down here until the structure is at resonance. Then, knowing the tank capacitance and the regulating coil inductance, he can calculate the frequency that he's operating at. From that frequency, he can then determine what the ball capacitance is at that height. But here's the problem. He uses the inductance that he measures at 138 hertz, and he uses the RF frequency that he's operating at, and the problem is this. The inductance at 138 hertz is not the same as the inductance at the resonator frequency that he's operating at. Here you can see, this is a summary of Tesla's own data. Here you can see the VFO frequencies that he has, and that's what he's going to use in this formula for capacitance. But he's going to use this value of inductance that he measured down at 138 hertz. And when he does, he determines that the capacitance of the ball is increasing as he raises the ball. And of course, that can't be true. And of course, when you look at Neumann's self-inductance formula, you find out, hey, wait a minute, you can't factor this current out to cancel it with the current in the base to get a simple geometrical formula for inductance in general. It only works in special cases. All right, the cardinal sin is that the Tesla coil is not a lumped inductor. And we've gone over this before, and you can actually plot the Tesla coil on a Smith chart. A Tesla coil that loaded with a ball is a transmission line, a velocity-inhibited transmission line, and has spatial resonances, not lumped element resonances. And wherever these zeros of the impedance, actually the reactance, are the series resonant frequencies for this system. And the current distribution is different at the different frequencies. For example, here we have a resonance at 175 kilohertz. Here's the resonant at 435 kilohertz, and then 600. And the current distribution is changing on the structure. This is the voltage distribution. It's changing as well along the structure. All right, here's the helical coil. And we're going to use the transmission line model for it, Tesla's actual physical dimensions. We calculate the properties of the helix. And then we'll use the actual values for the capacitance of a ball at these heights above Earth from classical electromagnetics. And at 8 feet high, we get a frequency, resonant frequency 329. Tesla measured 331. The difference is well under 1%. 10 feet, 33 feet, 57 feet. We know what the capacitance of the ball is. We calculate the frequencies and then compare them with the frequencies that Tesla measured. And we're on the order of 5% or less. This one at 10 feet is just a tad over. So here are the values that we calculate, the actual values for the capacitance of these values, the capacitance of Tesla's structure. So we think we've got the mystery resolved, and what it boils down to is the fact that we've got a distributed element circuit, just as Tesla described in his Belgian patent in 1897. So Tesla knew better. The question is, why? Why did he do this C of H experiment? Why was it so important to Tesla that he would spend almost a third of his time at Colorado Springs chasing this ball up and down the wire? Tesla said the ball could be pushed up and down and lifted to a certain height as I needed it. Why did he need it? Well, we found that if you do what Tesla said he did, you'll see what Tesla said he saw every time. Some experimenters who have gone after me have found a difficulty. They say, no, we can't replicate it. Well, it's not my fault. I never had the slightest difficulty. Anyone who has no more than my skill can do it. Thank you.